Welcome back viewers to our channel SNS Achievement Zone. This is Professor Dr. Abu Bakar Parvez from the Department of Agriculture Engineering. Today the topic which we are going to witness in our online class is the velocity triangles of a turbine. Before getting into the topic, the content delivery in this lecture series video will be as follows. We'll get to know what an hydraulic turbine is, the classification of hydraulic turbines, the hydroelectric power plant, the velocity triangles of a Francis turbine, then the velocity triangle of a Pelton wheel, and finally a Kahoot assessment for your perusal. So basically, a machine which converts hydraulic energy into mechanical energy is known as a hydraulic turbine. In orthodox, it shall be defined as an opposite of a pump also. There are a few examples of a hydraulic turbine mentioned here, like a Pelton wheel, a Francis turbine, and a Kaplan turbine. Previously, in our lecture series, we had put up a lecture on the various types of turbines, like Kaplan and Francis. Can anybody recall what is the difference between a Francis turbine and a Kaplan turbine? Yes, the difference is here. It's an impulse type and reaction type turbines. Impulse type is a Pelton wheel, whereas a reaction turbine is the Francis or Kaplan type. So what is this? It is based on a classification based on according to the energy at the inlet. In impulse turbine, the kinetic energy is maximum than pressure energy, and vice versa in reaction turbine. Apart from this, classification of a turbine can also be done with the help of the direction of flow through runner, like tangential flow, radial flow, axial flow, and mixed flow or mixes flow. So the water flows along the tangent, it's tangential. It flows along the radius, then it's radial. If it flows along the axis of the runner, it is axial, and all this combined, like inlet radial and exit is in axial, then inlet plus that's axial plus radial, it becomes mixed flow type of turbine. Then we have, according to the direction of the flow of the runner, these four which I have told in the last slide. Now, can anybody recall the difference between a Kaplan and a Francis turbine based on their heads? Last time the question was what was the difference basically. Now based on the heads, can anybody classify these two? Yes, based on heads, low head is below 60 meters, which is Kaplan turbine. If it's between 60 to 250, it's Francis turbine, medium head. And if it goes above 250 meters, the head, then it's a high head turbine, which is a Pelton wheel turbine. And based on the speed of the turbine also, we have like low specific speed, medium specific speed, as well as high specific speed of the turbines. Like below 60 RPM, it is low speed. Above 60, up to 300, if the specific speed lies, it becomes a medium specific speed turbine, and finally if it crosses 300 rpm, it is a high specific speed turbine. So here I have generally put up a layout of a hydroelectric power plant for your perusal. You can see there a reservoir, which is basically a dam constructed across a reservoir of a water body. You have a head race. Based on the head, we have given the various turbines classification, and you have a surge tank, you have a valve house to open or close the flow of the water, you have a penstock, and you have a tail race, and you have a turbine house through which the hedge and HF is calculated, and electricity is generated. So now I have a question: what is the need of a surge tank? Yes, I mentioned it in the next slide, where I have given a definition of the dam. What is it? A penstock, a pipe which conveys water from a dam to the turbine house. The turbine house is the assembly of the runner, the shaft which converts the hydroelectric energy into mechanical energy. That mechanical energy is actually converted into electricity energy. So here the answer for the question is like surge tank, a storage tank which is fitted on penstock before valve to avoid water hammer, the phenomenon of water hammer. To avoid that, the surge tank is very much useful. And valve house is to control the flow of water through the penstock. Now coming to our case study, that's the velocity triangle. In turbomachinery, a velocity triangle or a velocity diagram is a triangle which represents the various components of velocities of the working fluid in a turbo machine. Velocity triangles may be drawn both at inlet and outlet sections of a turbo machinery. So basically these are the terminologies which we have to be knowing in the while drawing the velocity triangles. A general velocity triangle consists of the following vectors: the v, which is absolute velocity of the fluid, and the angle which it makes that velocity entering inside is the absolute angle, which is the question which I have asked you people. This is the angle of the rotor blade, actually beta, and u is the blade linear velocity. V is the relative velocity of the fluid in contact with the rotor. V absolute velocity, called as the will velocity, the tangential component of the v, whereas the v velocity flow is the axial components in case of axial machineries. The following angles are actually incurred and encountered during the analysis and drawing of a velocity triangle. Alpha is the angle made by v with the plane of the machine, and b, as said, is the absolute angle of the rotor blade. So here I have shown a small diagram which represents a velocities involved. An example of velocity triangle drawn in the inlet of a turbo machine is given here, which I have drawn using a pencil. You can see the two angles there, alpha and beta, alpha 1 and beta 1, and the one subscript denotes the high pressure side, that's inlet in case of turbines, and outlet in terms of pumps and compressors. So velocity triangle can be drawn for a turbine as well as it can be drawn for a pump. Here we are drawing for the turbine. The subscript 1, it denotes the high pressure side, and you can see this diagram. You can see u1, you can see vw1, you can see v1, etc., which has been drawn. So these are the velocity triangles of a Francis turbine. The turbine runner, blade, inlet and outlet under different operation conditions are drawn. A is the maximum wicket gate opening condition, where it's open, and B is the peak efficiency condition, and finally its minimum wicket gate opening condition is given as C out here. And this is the velocity triangle drawn for a low speed turbine and a high speed turbine. You can see a difference out there. In low speed turbine you have V2 corresponding out there, whereas in high speed or inlet velocity triangle we don't have that V2. And when it comes to high speed, the V1 is perpendicularly drawn, showing the high speed of the water entering the turbine. And for a Francis turbine you can see a velocity triangle drawn out here using the R and R1 and R2 as the inlet and outlet velocities. You can see the angle taken out here. You can see the alpha angle, you can see the theta angle here, and you can see the Francis runner for high speed or for higher specific speeds. Then B, you can see second diagram, you can see the Francis runner for medium speed, and finally you can see it for low head and high head. It's a Kaplan runner as well. And finally I have shared a Kahoot assignment here for you people to know more about this velocity triangles as well as the working of the turbines. Thank you for listening to our lecture. The textbooks, references and web references have been given here for your kind perusal. Kindly comment your valuable queries or any sort of enquiries or questions so that I can answer it to you in your comment box. Thank you for listening, viewers. Have a nice day ahead.